Okay, so we know that Newton's first law says that an object's mass is related to its inertia. If there's no unbalanced forces, then the object will either remain stationary or will travel at a constant velocity, also meaning a straight line. Now, if something does change the inertia of an object, it would require a net force, an unbalanced force in some direction. That's where Newton's second law takes over. Okay? Newton's second law applies to all the situations where there is an unbalanced or net force. As soon as there's a net force, then there will be a change in velocity, thus an acceleration. Okay? And that acceleration, as we said the other day, okay, is based on a couple of things. Okay? Force, sorry, can you guys see that, or would red be better? Red better. So you get chromostereopsis though with red. Opposite ends of the spectrum does weird things. Okay. All right, so this is Newton's second law. Okay? The net force, that unbalanced force, F net, is equal to mass times acceleration. So as we were saying the other day, the acceleration is related to the net force divided by the mass. So the larger your mass, the less your acceleration. And we said that that's the reason why mass is the most important safety feature your car can have. The more of it you have, the less you will accelerate and the less you'll be injured as a result. So, if you don't have a choice on mass, then you have all those other things that have to do with Newton's first law. Seatbelt, airbags, okay, all the other crumple zones, all those other safety devices in your car that work on the acceleration formula we learned before. Okay? Every other safety device works on T. Okay? Works on making T bigger so that acceleration is smaller. All right? In the end, okay, this is the one that can determine, or is the big determiner of your acceleration. The amount of force applied to you and the amount of mass that you have. Right? Now, what I'm going to show you here is dash cam video of an accident my cousin was in. And she ended up with a broken pelvis and a broken femur as well. She was hit from the side, okay, by an SUV. The driver was distracted, okay, didn't see her pull out into the intersection and creamed her at high speed. Okay. Now, you can see what happens in terms of both Newton's first law. She wanted, the car that hit her wanted to continue going in a straight line, okay, but also the effect that mass has. She has a small car, okay? She gets hit by a fast-moving SUV, and you can kind of see the effect here, okay, when that happens. Okay, so she's in front of this Nissan. Okay, now, she probably would have been killed had it not been for this little car here. Okay, the driver caught the edge of this car first. Okay, now he hit the brakes right about here. Okay, so it wasn't much into it. Okay, but hit the brakes just a little bit. You can see, I'll back it up here. You can see where his tires lock up. Okay, so right here you can start to see the smoke coming out from underneath. Not quite there yet, but yeah, there you can see that's about one frame away. So he hits the brakes right about in line with that post for the traffic lights there, clips this car, which slows him down enough, and then he hits my cousin's car in front of that. Now this is in Hawaii, she lives in Hawaii. These traffic rails, in Canada, those are all made out of what? They're all made out of concrete. Yeah, we don't have the option of what they have in Hawaii, which is they make them out of plastic and they fill them with water. Okay? Since it never freezes in Hawaii, this is an excellent way to help absorb crash forces. Okay? Because when you hit these things, they deform and the water jets out, and it's like hitting a hard cushion. Not a soft one, a hard one. Okay? But it's a lot softer than hitting concrete. Okay? Now, we don't have the option. If we did this, it'd be great for about 3 months of the year, and then the other months of the year, they might as well be made out of concrete because they'll be frozen solid. Okay? The other problem with filling plastic objects full of water is that the water expands and cracks them, and then they're useless. So we can't really do that here, but it is a great crash safety thing that they use in places that are more tropical. Okay? And you can see that when he hits her, he pushes her car this way quite a ways, but it's actually these barrels, essentially, that are full of water that also help to absorb some of the crash forces and some of the speed of this car. Okay, so you can see there's quite a bit of penetration into the driver's side, okay, of her car here. I mean, here's the wheel. The tire is in the car. Okay, so there's considerable penetration. And what side of your car has the least amount of absorbency? The doors, right? Your car is, you're safer to get hit head on than you are from the side. Okay? There's more crumple area, okay, stuff like that to absorb the crash than there is from the side. Okay? From the side, you only have the thin metal of the door and the side curtain airbags if your car is equipped with those, and that's it. Your seatbelt doesn't do much good for you from this angle, right? So hitting from the side, getting T-boned is probably one of the worst directions to get hit from. All right. So dangers of texting and driving. Don't do that. It's dumb. Okay, and deadly. I know lots of people do it because I'm on parking lot supervision. And it drives me insane. It makes me want to throw things at them. But I'm not allowed. Because trust me, if I was allowed, I would throw things. Okay? I don't like seeing people get hurt, and that's one of the things that will get people hurt. All right. So, Newton's second law. Sorry. Okay. So the things we have to get out of today, we have to understand the relationship between force, mass, and acceleration. That's F net equals m times a. Okay? We need to understand how force and mass influence your change in velocity. That was this manipulation of the formula here. The bigger the force, the bigger your change in velocity. The bigger the mass, the less your change in velocity. That's the relationship. As long as we understand that, okay, we understand the gist of that part of Newton's first law. Or sorry, Newton's second law. Okay? And then obviously looking at solving problems related to Newton's second law. Now I told you last week we're going to spend like at least 10 days on Newton's second law. It's a huge concept. Okay? It governs everything, okay, in this unit and a lot of stuff even in the circular motion unit. So it's a huge law. Okay? So it's not as simple as F equals m times a. I mean, that's like saying, hey, we're going to spend 2 weeks on v equals d over t for mathematical difficulty. Okay? And while Newton's second law is not really mathematically difficult, there is a second part to it. Okay? And that is this. It has to do with the whole unbalanced forces thing. Right? So we can say certainly that F net equals m times a. But remember that F net is that unbalanced force. All right? So what we can actually do is there's another way to calculate net force if I don't have mass and acceleration, and that would be by the vector sum of all forces. Okay? So that means there's going to be some vector addition still here. Okay? The vector sum of all forces is the other way to find that unbalanced force by adding all the forces together. If they all add up to 0, then the net force is 0, and Newton's first law applies. If they don't add up to 0, Newton's second law applies, and there will be an acceleration in the direction of that unbalanced force. Okay? So a simple example of this would be like what we looked at on Friday with the book. Okay, so we had like a 2 kilogram book, okay, and it had a force of 20 newtons this way and a force of 18 newtons this way. All right, what do we call that diagram? Free body diagram. Okay, so this is kind of like your givens in a question. So I write a box, okay, to represent my mass. No matter what the mass is, draw a box. That way, if you're not artistically capable like me, okay, I challenge to draw a box. Okay, you just have to draw a box to represent anything and write the mass of the object inside the box. Okay, then you simply draw the forces acting from the center of mass. Sometimes you may hear that applied as center of gravity. Okay, you've probably heard that term before. Right, lower your center of gravity. You got to move your center of gravity. Okay, center of gravity really is center of mass because even in space where there's no gravity, I still have a center of mass. I don't have a center of gravity though, okay? So center of mass, okay, we draw the forces as though they're acting from that direction. Now, right now, if I do a vector sum of these forces, what I get is 20 newtons this way and 18 newtons this way, and I get a net force of 2 newtons to the right. Now, obviously, you wouldn't bother drawing a vector diagram for 2 collinear vectors like this, but hey, we're simplifying it because it's the first time. Okay, so I have a net force of 2 newtons acting on a 2 kilogram mass. Could I now calculate the acceleration of the book? Okay, this is my F net, right? I just did the vector sum of all forces in order to get that. So I now know what F net is. I know the book has a mass of 2 kilograms. F net over m equals a, 2 over 2, okay, equals 1 meter per second squared to the right. Okay, so that's what the book would do in that situation. Now, that's about as simple as they come. Okay? They do get a bit more complex than that as we go along. Okay? There'd be more and more forces, or there'd be multiple masses, okay? Or things like that. If there's multiple masses, then we call it a system. It's not just an object, it's now 2 objects or 3 objects, and now it's a system. Okay, and we're going to go into all of that. Okay, but within a week, we'll be looking at questions like this. Okay, I have a 15 kilogram mass sitting on a table. Okay, it's being pulled by a string at an angle of 20 degrees above the horizontal with a force of 50 newtons. There's a force of friction acting back on it of 5 newtons. Okay, and you got to calculate the acceleration of the object. Okay, so wow, that seems a little more tricky. Well, here's the thing. It's not that tricky. We just haven't learned how to find all the forces yet. Okay? We have this angled force and we have this force, but we also have gravity. We also have the normal force. We have all these other forces that are acting. Okay? And once we have them all, then we can figure out which ones cancel and which ones matter, and then from there we can find the net force. It becomes a vector thing, but we'll get there. Okay? All right. So, second law deals with what happens when there is a net force acting on an object. Again, I'm going to show you a video here. Okay, think about a hockey puck. When the player strikes the stationary puck, he causes the velocity of the puck to change, causes the puck to accelerate. Okay, the cause of the acceleration is the force that the stick applies. So, how long does a puck accelerate for when it's shot? Okay. This thing should only be accelerating as long as there's a what present? A net force. So, once the puck leaves the stick, assuming the ice is frictionless and it stays along the ice, the puck should do what? Okay. Keep moving at constant velocity, right? If the ice is frictionless and the puck and the stick is no longer pushing on the puck, now there are no unbalanced forces acting on the puck, and the puck would travel at a constant velocity until an unbalanced force like the boards or the back of the net or whatever, okay, are applied to it. Okay? But until then, it would travel at a constant velocity. In the real world, obviously, as soon as the stick stops pushing it, it's actually slowing down because there is friction, and friction would be the unbalanced force that would bring it to a stop. Right, so I'm going to show you this. Okay, it's kind of an old video here, but it's so we see then that puck starts to accelerate as soon as the force is applied. As soon as the force is gone, the puck is then going to have no net force, so it's going to travel at a constant velocity after that. Okay, now the acceleration, because of the way this formula is written, the force is directly related or linearly related to the net force. Okay? If I double the net force, what will happen to the acceleration? It'll double. Okay, as long as I don't do anything to the mass. Okay, so if I have that puck and I just give it a little push, it's going to accelerate a little bit. If I give it twice as hard a push, it's going to accelerate twice as fast. Okay, those two things are linearly or directly related. If I double the force, I double the acceleration. Okay, now the opposite is true for mass. If I suddenly double the mass, but don't change the force, my acceleration will be cut in half. Okay, so it's inversely related. All right. Okay, now lots of forces can act on an object simultaneously: friction and air resistance. Okay, so friction against the surface, air resistance from the air. Okay, they have an effect on the hockey puck. In such cases, it is the net force or the vector sum of all the forces acting on the object that is important. That's why we do that whole vector sum, okay, of all forces thing where we add all the forces together. Okay. Now, how many people have ever seen like 3- or 4-way tug of wars? Because they're actually a really good example of vector addition or vectored forces. Okay, normally we picture a tug of war like this diagram, right? Force that way, two teams are directly in opposition to each other. But you can do 3-way and 4-way tug of wars as well. You just put a ring in the middle, you tie all the ropes to the ring, and then all 4 teams will pull against each other. Okay, so if I have this mass here in the middle, okay, and I've got this team pulling with, let's say, 1,000 newtons, okay, this team pulling with 800 newtons, this team is pulling with 750 newtons, and this team is pulling with 950 newtons. Okay, which way is the center ring going to go? Yeah, it's probably going to move in the northwestern quadrant, I would assume. Okay. Now the way you win this is basically you have to get the ring to move to basically a circle. Okay. You have to touch the circle basically in your quadrants. Okay. So for this, okay, what I would do is I would take those forces and I would draw a vector diagram. So I had the 1,000 newtons going up. Okay. I had 800 going. Okay, this way. And then I had 750 going down. And then I had 950 going this way. Okay, so I just drew a vector diagram of my forces. Where does my resultant go? Right where we predicted, right? Into that northwest quadrant. Well, there is my net force. Okay, now, if I had said this many meters, this many meters, this many meters, this many meters, you guys would have done it like that. Okay? But as soon as I made it forces, suddenly it was a little different. But in fact, it's not. Okay? Vector addition is done the same for all vector quantities, including force. Right? So what we would know here is that from east to west, we have a net force of 150 newtons, okay, going this way, and our northerly directed one would be 250. So I didn't really draw that very well to scale, but okay, that's effectively what we have. Okay, we'd be able to calculate our net force and the angle at which it's acting. All right, so let's just quickly have a look at what that would be. Okay, so we got 150 squared plus 250 squared. Okay, so 292, but well, I'll say we have 3 significant figures here because we do. So 292 newtons. Okay, and then we could find that angle. Okay, so second 10 of 150 divided by 250. All right, so 31 degrees west of north. Okay, so now I've got my net force. question would probably ask me, what's the acceleration? Okay, well at that point, I would have to know the mass of that ring in the middle. Okay, so let's say that ring in the middle, okay, that they were all pulling on, okay, has a mass of 10 kilograms. Okay, so I want to calculate the acceleration of that ring. This is going to be unrealistic because it's going to be huge, right? But okay, 292 newtons, okay, there. So acceleration is F net over m. So 292 divided by 10 kilograms, 29.2 newtons, okay, in that direction. Now, what we would truly have to do here is also factor in the mass of everybody. Okay? The mass of all the teams would actually also make a difference because you're also trying to pull the teams. So you need all their mass as well in a question like this, what we were just trying to simplify. Right? Then we kind of follow how we do this as a vector question. Okay? So same vector addition principles as last unit. Okay. How did I get the what? Oh, okay. So I just did the net forces for the x's and y's. Okay, so I had 800 to the east, or to the right, okay, and 950 to the left, so the net was 150, and then 1,750, so 250, yeah. Okay, all right, so that's one of those ones that would involve doing vector sum of all forces. All right, so in Newton's second law, the net force is only one of two factors, obviously, that influence the acceleration of the object. We know mass also plays a role. Okay, if you were in my science 10 class, you've seen this diagram before, okay? If I have a person with a golf club and they're winding up with their best swing, okay, to hit that golf club, the golf ball, they're exerting this amount of force on a very small mass, which will produce a very large acceleration. Okay? The ball will accelerate off the face of the club at a very high rate. If, for whatever reason, they decide they're going to take that same perfect swing, wind up and smoke this truck, okay, well, now same force, huge mass, tiny acceleration, right? In fact, would we be likely to see that truck move at all? In the real world, no. Okay? Now, if that truck was on a frictionless surface, yes, you would see a very, very small acceleration, right? And, frictionless surfaces are not all that impossible. In the teacher parking lot last week, there was a nearly frictionless surface. Because every time I would try and park my truck, I would slide out of the parking stall, okay, after I put it in park, okay, because that ice was really polished, okay, and we would just slide forward. So if it was perfectly frictionless, then yes, the truck would accelerate. In the real world, just because the truck doesn't move, does it mean there's no acceleration? It doesn't, okay? An acceleration can even be a change in shape. Right? So, would there be a dent in the truck? Definitely. That would count as an acceleration. Here's the other thing. If I get the truck to move, every particle in the truck moves in unison. They all accelerate as though they're one big particle. That's not going to happen in a truck. It's huge. It's made of many particles. If I'm standing at the front of the truck with my hand on the front of the truck, do I know when it gets hit? What will I feel? When he hits the truck, what's going to pass through the truck? A vibration, exactly. Okay? Every particle in the truck gets accelerated when the club hits it. They just don't accelerate in unison. Okay? The vibration, the force, the acceleration is transferred to all the particles of the truck. Okay? And there will be a vibration that passes through the truck and can be felt by somebody on the other side. Okay? That can count as an acceleration as well. So we don't necessarily have to see an object move for an acceleration to be present. We're not going to deal with any situations like that because we're going to do simple mechanics, which means the truck moves ever so slightly. All right, so when a net force, or F net, acts on an object of a certain mass, the acceleration that results is directly proportional to the force and inversely proportional to the mass. That is Newton's second law written out in words. Okay? The direction of the acceleration is the same as that of the force. All right, so whatever direction the net force is in, that's the direction the object's going to go. So its acceleration and its net force are always the same. In the same way that in the last unit, displacement and velocity always had the same direction. Okay? One causes the other. Okay, units for force. So when we calculate force and we multiply mass, which is in kilograms, by acceleration, which is in meters per second squared, we get kilogram meters per second squared, which we mercifully abbreviate newtons. Okay, you still have to remember that a newton is a kilogram meter per second squared, but you don't have to write kilogram meters per second squared every time you do a force calculation. Okay, newtons, capital N, will be fine. Is 1 Newton very much force? It's not. Okay? 1 Newton is a very negligible amount of force. Okay? You probably not even notice it. If you were outside over the weekend, the wind would have been exerting much more than that on you. Okay? If you were walking around outside. All right. Questions so far? Okay. So what we've got here is that net forces cause accelerations. Those accelerations are in the same direction as the net force. Okay? Force is directly related to acceleration. So if the force doubles, acceleration doubles. Okay? Force or acceleration is inversely related to mass. If mass increases, acceleration goes down. Okay? And then also that net force is not just mass times acceleration, it's also the vector sum of all forces. All right, so free body diagrams, we've already talked about those. This is just a kind of a quick review. We do not draw free body diagrams with the forces acting into the center, okay? We draw them acting from the center, right? We put the mass in the middle of the box, and we draw the forces as though they act from the center. Okay? And all they do is help us to identify the forces that are acting on each other and help us to see if any of them would cancel and thus not have to be in a vector diagram. Right? So if I had a situation like this, okay, where I have a box sitting on the floor, okay, and it's being pulled this direction by 200 newtons of force. Let's say the box is 20 kilograms. Okay, well, what are the other two forces acting on this box? Gravity is one of them, yeah. Okay, and it would be 196.2 newtons, okay? And there'd be this normal force, force of the floor. How big is that? Equivalent, yeah. Okay. Otherwise, if it wasn't, there would be a vertical acceleration. And the last time I checked, when I drag something along the floor, it doesn't fly off the floor or fall through the floor. Okay. So this force and this force, okay, are equal. So what does that mean for me when I calculate net force? It means I don't need to include these in my vector diagram. I could if I wanted to, but what's the point? Okay. If I draw a vector diagram and I include those forces, I go, and then I go here, well, I don't need those, they cancel each other, okay? I just need that one force that's not balanced, okay, on there. Now, if there was a frictional force of, I don't know, let's say 90 newtons, okay, well, then now I've got to draw that one on here. I didn't draw that to scale very well, but, okay. Now I know my net force is 110 newtons. Okay. Simple vector diagrams. Everybody all right with that? All right. I want you guys to write this one down. This is a super simple Newton's second law, but requiring vectors type of question. All right, so here's the information they're giving us in the question. First off, they're telling us the car has a mass of 1,850 kilograms. Perfect. This is my car. 1,850 kilograms. All right, the two people that are pushing on it apply forces of 275 and 395 newtons respectively, and they both are forward. All right, so I would have 275 newtons, 395 newtons, and it says a third force of 560 newtons, the force of friction, also acts on the car. This force, however, is acting in the opposite direction of the pushing force. All right. Okay. Now, I try and represent the magnitudes as well with the length of the arrow, same as we always do. All right, so I've drawn my free body diagram, which is essentially my givens for this question. I want to calculate the acceleration of the car. What am I going to need if I'm going to calculate that? I'm going to need net force. Okay, now I have two ways to calculate net force. This way, which is useless to me right now because I don't know what the acceleration is, okay, and this way. The reality is you're going to use both of those in pretty much every Newton's second law question. You're either going to have the acceleration, be able to calculate net force, and be asked to calculate one of the forces acting on the object, or you're going to have all the forces and be asked to calculate the acceleration of the object. One or the other, but you're always going to end up using both. All right, so I want to find the vector sum of all forces. This is how I'm going to represent this. I'm going to say this. F net equals m times a, which equals 275 newtons plus 395 newtons minus 560 newtons. Okay? Rather than draw a vector diagram for three collinear forces, I'm just going to represent them as positive and negative and add them together. Right? What do I get, 110?
Yeah.
All right, so I get a net force of 110 newtons. Okay, that equals m times a. Do I already know what m is? All right, so I can calculate the acceleration then. Okay, the acceleration is going to equal positive 110 newtons divided by 1,850 kilograms, which was the mass of the car they gave me in the question. All right, so 0.059, we have three significant digits in this question. So 5.94 times 10 to the minus 2. Sorry, 5.95 times 10 to the minus 2. Okay, is that a very big acceleration? It's 6 centimeters per second. Okay, so every second you push on the car, it'll go 6 centimeters per second faster. Now, that may not seem like much, but if you keep pushing the car, it adds up eventually. Has anyone ever done this to start a stalled car? Okay, you can only do it with a manual. Okay, you can't start a car on compression if it's an automatic because you have to get it going at least 30 clicks an hour.
Would it be fine if you just left it like 0.0595?
Yes, that would also be fine. Okay, as long as it had 3 significant digits. All right, so does that one make sense to everybody? Okay, so that one involves a little bit of vector stuff. There's still collinear. There's nothing really big in there. Okay, but all of your Newton's second law questions will break down to this at some point. Okay, the vector sum of all forces equals m times a. Either you have m and a, and you're looking for one of the forces, or you have all the forces, and you're looking for a. All right, so that's what we just did there. Let's skip over that. All right, now this one involves some vectors, like some trig. Right? So I'm going to give you guys a few minutes to try this one. So we have a 15 kilogram block, okay, on a flat, friction-free horizontal surface. Okay. 2 forces are acting on it, a 35 Newton force acting 60 degrees above the x-axis, and a 10 Newton force acting directly along the x-axis. Okay? We want to find the acceleration of the block. right? So I would say that this one here, you just want to ignore that part of the diagram. What kind of diagram is the top? It's a free body diagram. It's a poorly drawn one because it doesn't have the mass in it. It doesn't have the forces labeled. Okay. If I was doing this, okay, I would have it look something like this. Right. We know it's a 15 kilogram block. Okay. We know there's this force here. Okay. Directed 60 degrees. It's 35 newtons. Okay. And then there's also this force. Okay. That's 10 newtons. So those are my two forces. I want to get the acceleration of the block. Okay. Going to have to do a little bit of vectors, and F equals m times a. All right, give you a couple minutes on that. Okay, so we've got our free body diagram. Now we need, if we're looking for A, we need m, which we have, 15 kilograms, and we need F net, which we don't have yet, but we can get because we can do the vector sum of all forces. So that'll be our next step. Okay, we're going to have this vector here. Okay, this is 60 degrees. 35 newtons, this will be y, this will be x, okay? And then we'll have the 10 Newton force on the end of that. Like so, that means our resultant, which in this case represents our net force, is going to look like that. And it'll have its own theta, its own y, and x. All right, so our next thing then is we need to find y and x for the black one. Okay, so that'll be x is the adjacent side, so that'll be the cos of 60 times 35, which is 17.5 newtons, and that'll be that'll just be positive because it's along the x-axis. That's all they gave us. Okay, y will be the sine of 60 times 35. I don't remember what that is. Sine of 60. Times 35, so 30.31 newtons, and that one's also positive because it's along the positive y-axis. And then obviously x for the red vector is 10 newtons, and y for the red vector is 0 newtons. Okay, this will be positive here as well. All right, so our overall x is 27.5 newtons positive, and our overall y is 30.31 newtons, also positive. Everybody with me there? Okay, that's just vector addition. That's why I went through it so fast, because you guys already know how to do that. Okay, so I've got my vectors. Okay, I've got my resultants triangle. So now I can calculate my F net, at least the magnitude of it right now. Okay, with Pythagorean theorem, so 27.5 squared plus 30.31 squared will give me my net force, the magnitude of it. Come on. Okay, so that squared plus 7 squared. All right, so we're looking at 40.93 newtons. Okay, for the magnitude of my net force, I want to get the angle of my net force, so that'll be 10 to the minus 1 of the opposite side, which is 30.31, over the adjacent side, 27.5, okay, to get my angle. All right, so that's all just vector addition stuff, all stuff we've done before. Okay, so okay, so we're looking at a vector of 47.8 degrees. Okay, and that's above the x-axis because that's all they gave me. All right, I'm not done yet though. All I calculated was the net force. What did they want? They wanted the acceleration. All right, so now I take this information here and I plug it into this. F net equals m times a. So acceleration will equal 40.93, my F net, divided by the mass, which was 15 kilograms. Okay, so we're looking at an acceleration of 2.7 meters per second squared. I think we only have two significant digits, right? Yeah. So 2.7 meters per second squared at 48 degrees above the x-axis. Okay, that would be my final answer there. All right. So just like questions we did in Unit 1, except there's an extra step at the end where I have to take the number I get, my resultant, and divide it by mass. All right, questions on that? Okay. Now, sometimes a Newton's second law question will have a part 2. So using the information you just calculated, I want you to calculate the displacement of the block, assuming it is stationary at the start, and the force acts for 8 seconds. Okay, so think about what you just calculated. Okay, you have the acceleration. They're telling you that initially it's stationary, and they're looking for how fast it would be, or sorry, the displacement of the block after 8 seconds. Okay, so anytime there's a net force, the object is going to accelerate, and getting in an acceleration question as a part B would be perfectly reasonable to expect. All right, so here's what we know. VI is 0 meters per second. Our acceleration we just calculated to be 2.7 meters per second squared. It was 2.7, right? Yeah. And that was at 48 degrees above the x-axis. Okay. And we know that the time is 8.0 seconds, and we're looking for the displacement. All right, so a formula we could use there would be D equals VI times T plus 1/2 AT squared. All right, now I'm saying that you might be asked to calculate the acceleration and then do this as a part B. There could also be a situation where I give you all this information, you have to calculate acceleration first, and then calculate one of the forces involved. Okay, it could go backwards as well. Okay. All right, so we've got VI, which we said was 0, so we can just get rid of that. And this is just 1/2 times 2.7 times 8 squared. And you'll notice I'm using the rounded value here. Okay, I'm going from part A to part B. The significant digits are already done. I use that calculated rounded value carried over to part B. Okay, not all of my decimals. All right, so we're looking at 86.4, so we only have 2 significant digits here, so 86 meters. Okay, everybody all right with that? Oh, what's wrong with that? There's no direction on that. Okay, at 48 degrees above x-axis. See how easy it is to forget? Okay, it did ask for the displacement of the block. Right? Displacement's a vector quantity. All right, questions on that one? All right, this is absolutely the easiest Newton's second law question you could ever encounter. All right, so in this question we have a lacrosse player who exerts an average net horizontal force of 3 newtons. What did they just give me? They gave me net force. They didn't make me calculate it. Okay? So I already know what F net is. F net equals 3.0 newtons forward. Okay? On a 0.15 kilogram lacrosse ball. So they just gave me the mass. Okay? Calculate the average horizontal acceleration of the ball. Okay, well, F net equals m times a. Gee, I wonder what I do. Right? So I manipulate here, get m over here, and I'm going to have that 3.0 divided by 0.15, and that should give me 20 meters per second forward. That's the last time you'll ever see one that easy. Okay? I mean, that's like a v equals d over t question. That is beneath you. Okay? I will not insult your intelligence by giving you one that easy every day. And some of you are going, please insult my intelligence. I would love to have easy questions. Okay. All right, I want you guys to try these two. They're pretty straightforward. Like number one is just as easy as the last one we just did. Okay? And number two is pretty much as easy as the first one. You just have to manipulate. All right, so we're going to walk through this one together. Okay, it's kind of like the car question we had initially with multiple forces now. Okay, so we have athlete A, who has a mass of 65 kilograms, athlete B, who has a mass of 70 kilograms, and the canoe that has a mass of 20 kilograms. What do I have to do with those masses? Add them. Okay, it's not just the canoe they're accelerating, unless they're not in it. Okay, and they're in it, so they count as part of the accelerated mass here. Right, so I need to first calculate my total mass. Right, so 65 and 70 is 135, 155 kilograms, okay, is my total mass. All right, so now I can draw my free body diagram, squarest canoe ever, okay, 155 kilograms, and now I can put the forces on there. So athlete A is going to row with 400 newtons forward. Okay, and athlete B, 420 newtons forward. And there's water resistance of 380 newtons. All right, so now I've got my free body diagram drawn. Okay, I want to find the acceleration of the canoe. All right, what's my next step? I have to add the forces. I have to get my net force, so vector sum of all forces here. All right, so F net, because they're all collinear, it is just a matter of going 400 plus 420 minus 380. Okay, so 440?
Yeah.
Okay, so 440 newtons, positive means forward. All right, now that I've got that, now I can calculate acceleration, F net divided by mass. Okay, 440 newtons divided by the mass, which was 155 kilograms. All right, so 2.8 meters per second squared forward. Actually, we have three significant figures there, don't we? 2.84 meters per second squared forward. Okay, so what's the mistake people make on this one?
The direction.
Nope, most of the people remember the direction. Not adding the rowers. Yeah. Okay. It's just a matter of perception, right? They read the question, they're thinking about the canoe and just the canoe, and they forget there's people in the canoe. And the most common mistake there is to forget the mass. So that's what that question is illustrating. If you are given multiple masses, you need to really look at the context of the question to see if you need them all. Do they need to be added up? Do they all matter?
For the significance, if for the mass you add with those numbers, would that count? But because the numbers up there that you add to get the mass.
Right. Okay, so here's the answer on that one. When adding, it's about decimal places, because that's how I determine the accuracy. So I still have 3 significant digits on my mass because they were all measured to the nearest kilogram, and when I was done, I had 155 kilograms. So that's a good question. I wouldn't give you one where there was a obscure, weird rule like that. That's why the answer does still have. Okay. Any other questions on that one? Okay, so I want you to go through this question. This one's got a fair amount of reading, and there is some extraneous information. That means information you don't need in this question. So they're going to tell you some things you're not going to use. So you got to sort through, kind of like reading comp. Okay, you got to sort through everything and find out what's important. I'm not going to make you find hidden meaning. Okay, that's not what physics is about. Okay, there's no hidden meaning here. You just have to figure out what's missing, okay, or what you don't need, what's extra in this question. All right, so the big thing here, in the man's 4-man bobsled, the maximum mass of the bobsled, 2 riders and a pilot and a brakeman is 630 kilograms. Cool. Don't need it. Okay, during the pushing, only 2 of them are in there. Okay, 2 of the guys are pushing. Okay, the pilot and the brakeman are already in the sled in this question, not all of them. Right, so it says here, okay, during a practice run, riders A and B exert forces of 1,200 and 1,220. They accelerate the bobsled 225, the pilot 98, the brakeman 97. Then they jump in for the challenging ride down the 1,300-meter course. Also, cool, don't need it. Okay, not important. All right, friction is 430 newtons, okay, and we're looking for the average acceleration. All right, so what we have, okay, is our bobsled, the brakeman, 323, 421, right? 420, sorry, 420. 420 kilograms is all the mass being accelerated by 1,200 and 1,220. And then, of course, resisted by 430 newtons. Okay, we calculate our net force, adding those things together. Okay, so 1,200 plus 1,220 minus 430. Our net force is 1,990 newtons. Okay, equals F net, and then I can calculate the acceleration by taking the 1,990 newtons and dividing it by the 420 kilograms, and that will give me my 4.7 meters per second squared forward. All right, so important to read the question and get what you need from it. All right, I'm going to come around and spray the desks. If you guys can wipe them down, please.